I'm James Servos. I'm the engineering manager for perception here at OTTO Motors. I'm here with Jay, who's the VP of product. And we're excited to talk to you a little bit about what we do at OTTO Motors and some about the applications of machine learning in mobile robotics. So first, just some background about the company. OTTO Motors is actually a division of Clearpath, which also includes another brand called Clearpath Robotics that many of our research partners or academics in the audience might recognize, our iconic yellow and black robots. The Clearpath Robotics side of the business makes robust platforms for mobile robotics research and was actually the original focus of the company. In 2015, to support the growing demand for industrial robotics, we spun out OTTO Motors, which is the division that does handling self-driving vehicles and industrial materials handling. So a little on the Clearpath Robotics side, as I said, they do robust robotic platforms for researchers. They come in a variety of sizes, from our little Jackal all the way up to an 8-wheeled all-terrain vehicle. And they do customizations for anything that researchers need. And this allows researchers to focus on the important aspects of their research and not having to worry about the details of making a reliable robotics platform. But for the majority of this presentation, we will focus on OTTO Motors, which is our industrial brand. And we create fully autonomous self-driving vehicles for infrastructure-free navigation for industrial materials handling, which is just really the fancy way of saying that we make vehicles that carry stuff around facilities for our customers. Really, they can operate in any kind of a variety of wide use cases in different environments and factories and warehouses. They're used in a huge amount of applications in different industries like automotive, industrials, retail and distribution, aerospace, among many others. We have two main products, the OTTO 1500, which you see on the left, which is our heavy-duty industrial transport for large payload, very heavy loads, and really just heavy-duty workloads. And our smaller vehicle that you see on the right is our OTTO 100, and it's for obviously lighter payloads in smaller spaces, tighter corridors, and smaller loads. Both can be customized with different payload attachments. So you can see there's a lift, robotic arms, conveyors, or carts to really service a whole wide range of different applications. The automation industry is really taking off. It's exploding, specifically mobile robotics, as Forbes said in 2019. It's taking off like a rocket ship. And there's really four main reasons that people really want to get into industrial automation. The first one, which may not be obvious to a lot of people, is there's actually a labor shortage in a lot of these industries. A lot of companies just can't find enough people to work in these jobs. So we're using automation to really fill those gaps. The second one is safety. So for safety, we're looking at workplace accidents are a big concern for most companies. And the most often the cause of these accidents is human error. So we can automate a lot of these jobs. We can eliminate that human error, and we can make the workplace safer for everyone involved. The third big point is the digital transformation. The modern world is all about data, and industry is no exception. So industry wants to know every detail of what's going on in their facility, and automation helps them keep track of all of that information and really keep up to date on everything they have going on. And the final big key is flexibility. Adding fixed infrastructure to facilities can be expensive. It can lock you in to that setup for a long period of time, and particularly in these really troubled times where things are changing constantly, the ability to be flexible in your facilities and your manufacturing and your warehouses lets you adapt to the changing needs of your business as things in the world progress. At OTTO Motors, we have large fleets of vehicles deployed all around the world. We have over 90 active sites globally, which are all different environments, different use cases, and our robots really have to be robust to all of these different cases. We have hundreds of thousands of autonomous kilometers driven. We like to say that it's around 25 times around the world that our robots drive every year. So we're getting lots of data as we go, and over 400,000 missions or tasks are completed by our robots every month. Our robots are operating 24/7, completing tasks and really adding value to our customers. And we provide consistent, reliable work that our customers can really count on. let's talk a little bit about the technology that goes into these robots. So OTTOs are very complex, intelligent machines. They rely on dozens of interconnected systems to intelligently make decisions and perform tasks. Some people assume when you say AI that it's going to just be one big neural network that's doing end-to-end control and perception. In reality, the end-to-end learning is really not feasible for a production system at this point, at least not yet. Maybe someday we'll get to that point. But for now, we have a very deep software stack that extends from the highest levels of fleet management and coordination through our autonomy core that includes perception and navigation, all the way down to really low-level motor controls and controlling the outputs of our vehicles to produce the results we need. And all of these pieces work together to create an intelligent robotic system that can operate in a wide range of challenging environments and really make intelligent decisions. But for now, and obviously for the focus of this presentation, let's talk a little bit about the applications of machine learning. So as I said, we can use machine learning to really enhance a whole bunch of different aspects of our overall system, from all the way from the top to the bottom. And it's not just about some of the more obvious applications. There's a lot of parts that can use these techniques all the way through the stack. So let's look at a few of those. So starting at the top, we have fleet management. So the fleet manager is really responsible for high-level coordination of all of our vehicles and all of the resources in the system. We can use machine learning techniques to optimize the performance of the overall system by changing that mission allocation, optimal charging cycles, traffic management, and facility integration. And really, by controlling all these and learning how the system is operating in different environments, we can enable and ensure that the resources are allocated in the most efficient way possible and get the most work done with the least amount of vehicles or resources. Next up, we have data analysis. So as I said before, in the third reason that people really want automation, it's all about the data. And some people like to call it the IoT for industry or Industry 4.0. And it's about collecting all the big data analytics about what's really going on in your facility. And when we add autonomous vehicles, they can really act as mobile sensor platforms in these environments and keep streaming all kinds of great data back to us. And we can leverage this data to learn models that will not only optimize our robots, but the overall facility itself. And we can gain insights into the process that's going on, whether it be manufacturing or warehousing, optimize the system, and really make sure that everything's running as smoothly as possible. Simulation. So simulation is not really an application of machine learning, but it's definitely a critical part of any machine learning pipeline. This allows you to collect thousands of hours of simulated runtime in a fraction of the real world time, which really allows for much easier generation of ground truth data. And you can collect large amounts of data in a short amount of time and makes it much more feasible to start prototyping these large machine learning algorithms without really having to invest the large amounts of money it takes to collect real world labeled training data. Mapping. So the state of art of SLAM these days is yet to really be taken over by machine learning. Although many people in the field are trying their best, it's really still dominated by model-based methods. However, we can augment these model-based methods in a lot of different ways by integrating machine learning approaches and information that can benefit us in a lot of different cases. So as you can see here, we're really adding semantic understanding of the environment to these mapping methods, which can improve mapping so that we know, what we're looking at, what's dynamic, what's going to be there the next time we come around, and really give the robots the ability to understand what's around them, which not only improves their interaction with these things, but also their robustness and reliability in these highly dynamic spaces. These are some of the cornerstone applications of machine learning, some might say, but detection, classification, tracking, prediction. These really are the things you see the most often in the machine learning space. In mobile robotics, obviously, they're also very important. There's many things in the environment that we really want to be able to track reliably so that we can interact with them and make intelligent decisions. These include stuff like forklifts and other vehicles, so that we can make intelligent traffic decisions and operate around them effectively. Detecting humans so that we can interact safely in close quarters that we often are doing with our robots. There's often people very near to us, and we want to be able to safely interact with them. And in more detailed cases, stuff like pallets. Often we need to be able to interact, pick up, move various goods, including pallets. So being able to track them and detect them effectively is obviously a very important part of our system. Next, planning and navigation. Similar to mapping, planning is still well grounded in the model-based methods, but we can, in the same way, leverage a lot of additional machine learning information. This includes stuff like local traffic management to make our robots much better at navigating around each other and making a more reliable system in that way, as well as obstacle detection and drivability analysis, being able to detect what surfaces we can drive on, what we can't, and really making a much more reliable system for detecting small and challenging obstacles. This really enables us to make much more intelligent behaviors and really improve the overall performance of the vehicle. And at the bottom of the stack, we have vehicle safety and controls. So consistent, reliable vehicle control is obviously critical to being able to effectively navigate a vehicle. So adaptive controls enables us to do this and account for changes during the operation of the vehicle. Autos can perform many different operations. As you can see in the pictures, we could carry small bins, or we could be carrying an entire other vehicle. Obviously, this is going to have major changes on center of gravity, traction, weight, that we need to be able to account for when we're doing controls. Same with wear in the vehicle over the lifetime of its service. So using adaptive controls allow us to have consistent and high quality control of our vehicle, no matter what conditions it may be operating in. There we go. And finally, there's obviously ongoing challenges, and many of which reflect the greater efforts that are going on in the machine learning space as a whole. It wouldn't be a machine learning presentation without someone complaining about not having good quality data, so I will be no exception. Getting accurate, sustainable data collection that we can annotate is obviously vital to any AI pipeline. So that's obviously still the case for us. There's additional challenges with robots. The robots are not here. They're in some remote facility somewhere. We have to be able to get that data back. We have to be able to annotate it. So there's an extra layer of challenge when you're working with robots. Another common machine learning challenge is obviously generalization. So we don't want to have to retrain our networks every time we deploy in a new building. So we need our networks to be generalizable to all variety of spaces that they might be deployed in, and adaptable to that wide range of environments and a wide range of use cases. And finally, a big thing for us is safety. So safety is critical, as I mentioned again, and one of the top 4 key reasons people automate. So we have to make sure that anything we make is safe and reliable. And in the terms of machine learning, that usually comes back to explainability and really understanding what the networks are doing. So we have these big vehicles that are going carrying heavy weights, going pretty fast. We need to be able to understand and expect what they're going to do and make sure they don't do anything unexpected.
Yeah, James and Jay, can you talk a little bit more about mobile robotics versus normal robotics?
Normally, when we're talking about mobile robotics, we're talking about robots that aren't hard mounted. So industry has had robots for a long, long time, right? We've had robotic arms. They're bolted to the floor, and they've been welding cars for years. When we're talking about mobile robotics, we're talking about robots that aren't fixed. So they have, in our case, they have wheels and they can move around. They might also still have arms on them, but it gives them a lot more flexibility. It means that you can rearrange your factory. They can go to places that a bolted down arm might not be able to go to, and really do a lot more things. And obviously, it adds a lot more challenge to what they can do, because they could be moving around and really interacting with a lot of different parts.
Yeah, cool. No, thanks for that.
And there's been a few phases of that, if you think about it. Like James said, originally things were just mounted, right? But then we've had robots that could follow magnetic lines, or robots that could position with sensors, or robots that might, have a human drive them through and then be able to repeat that again and again. What we're now at the stage at with what OTTO and some other companies are doing is robots that are self-driving. Right, they're not just mobile, but they're intelligent in making their own decisions without physical guides and without having to have done the thing in the past. If it has a map and it has sensors, it can go make its own decisions and do the job. And so it's more of a continuum than just one or the other. And it's pretty fascinating to watch the technology kind of reach the stage of that.
I was curious. I mean, I've seen and kind of grown up in the last kind of 30 odd years or not 30 odd years, maybe the last 5 to 10 years, seeing Boston Dynamics and all the crazy stuff they're doing with the robots doing backflips and stuff like that. What was the kind of the product decisions around? Have OTTO Motors ever thought about like a forklift that kind of literally does the heavy lifting as well, or kind of putting little robot arms on it and kind of carrying it? What was the product and the ideation around that?
Yeah, so there's a lot of really awesome things that people do with robots, and some things are very, very splashy and very, very cool, and some things are very, very practical. Maybe some might even say dull, although James and I wouldn't say dull. And there's there's a continuum along, and sometimes there's sort of the ability to work them both together. So, for example, there's somewhere out there's a YouTube video of the Boston Dynamics robot where it's going around and doing kind of the Segway type motion, picking something up and putting it down on an alley, right? And so there's kind of partnership. These things are not mutually exclusive. Where we are working on forklifts, there's video of that out there. Some early stages of forklift project. But basically, yeah, it's just about building the skills up, right? So the idea is, we didn't just come out of business now. We came out of business like, it's the auto division, 5 or 6 years ago. Mm-hmm. And the idea is to do things that are simple, repeatable, and valuable,
mm-hmm.
And then you build up. You build customers, you build revenue, you put more money in R&D, and bring great people like James on board, and then you build that skill set up further and further. And so now we're at a place where we could do things we couldn't have imagined, half a decade ago. And so the product decisions are really just about how to do an orderly introduction of features. So you order the R&D and make things that you can sell and do real work with.
Yeah, no, that sounds like a very kind of business decision. It's like, no, Adam, we're not putting arms on our robots. We don't need arm robots yet. But can certainly see, kind of the forklift function of it. Yeah, definitely. Yeah. We have a question from Lou. Lou has asked, how do these robots compare to the ones we see in the Amazon warehouses?
So the Amazon robots actually have a bunch of differences. So the big one is that most of those Amazon warehouses are human exclusion, so you can't actually walk around an Amazon warehouse that has those robots working in it. Unlike our robots that are with humans interacting with them in the same workspaces, Amazon robots bring the goods to the person and there's kind of a line drawn in the sand. The other big thing is that they are very infrastructure heavy, so that you have to have the warehouse has to be built in the Amazon warehouse style that has markers on the floor with Amazon shelves, with Amazon boxes, and all in Amazon ways. So I would just say that Amazon's is tailor-made for Amazon, whereas ours is more of a generalized solution for all in industry.
Awesome. Yeah, great answer. And good question there from Lou. Got a question from AJ. AJ has asked, do you see resistance from employees in deploying these robots in the same environment they operate in? Yeah, good question, AJ.
Not really. I mean, anytime you have new technology, there's always skepticism, and people kind of want to test it. People are, some people be afraid, some people be curious. Like you'll have some people, jump in front of things and see if it's really safe. It turns out it is, which is good. But what's important is that we're, like James said in his presentation, there's a lot of places that can't hire people fast enough, right? And it's not that, people are losing their jobs. It's like people are not getting hired fast enough and not moving the things that need to be moved in order to make industry work. And so now something comes along, and that work that was a distraction to you before, or you were getting pulled away from your real job to go move something, and now the robot's moving it for you, like, that's awesome, right? There's also stories of people that have moved from materials handling to other positions that they couldn't fill before, because you just can't stop doing materials handling. The robot helps you do that. And so, job satisfaction and pay can go up as a result. The common phrase that we start hearing from people that have been using the technology for a while is, robotic coworker, which I think is a nice way of putting it. And I've been in sites and I've seen people like stop for a robot and like wave it through or say hello to it, right? You get into a whole really interesting field of human-robot interactions and anthropomorphization, and there's always new technology, always new things have challenges on adoption. But I'd say that the path is a very, very positive one. People enjoy where they get to.
What was that word you said, Jay? Anthropomorphization? Tell us about what that means.
Oh, it's like, people will tend to, it's psychological, right? People will tend to imagine human-like qualities into other things, right?
Sure. Like, so kind of waving the robot through. It's like, I don't know if it knows hand gestures or...
Yeah, it doesn't care. If you
Get me a coffee, Otto.
It doesn't care if you wave and say hello. But it makes the people feel better. And we've seen studies where the more people work with the robots, the more they tend to do this. Right, so the architects may not think about the robots that way, but the operators do. It's kind of an interesting phenomenon.
It kind of verges on that kind of ethics and that. What was that test? The AI test, where they test to see if it's got that human quality. The Turing test. The Turing test. Really, I think that's another kind of can of worms. Let's jump to our next question. Thanks. Sorry, what was that, Jay?
I don't think we're passing a Turing test anytime soon.
Yet. Maybe 2025 Auto Motors when you got hands on it and a little smiley face. Let's jump to our next question from Ali. Ali has said, do you do automated data collection, like any facing an obstacle, collecting the data and send it to the cloud? And do you use mechanical Turks for annotation? Why not overfit to the environment where we can?
So the short answer is yes, we do a lot of data collection. We do have to take into account privacy concerns in a lot of cases. You can't just videotape all the time and send the data back, because that's not okay in terms of privacy. So we're very cognizant of that. But when we can, especially at beta testers or our private facilities, we do automated data collection all the time, and we're piping as much data as our internet bandwidth can handle back to us. So yes, it's a big thing. You always, I joke, but data is the key to all of this. So you always need more. In terms of Mechanical Turk, yes, we do use third-party labeling services for a lot of our labeling, just because it takes a lot of time for anyone that's tried to do data labeling on their own. So we outsource it, as many of the big companies do, and really just pump through it as fast as we can. But data quality is always a big concern with any of those type of outsourcing. So you really do still need to comb through it to make sure you're getting the highest quality data. I forgot what the last part of that question was.
He said, why not overfit to the environment where we can?
So you could overfit if you pipe the data back and you had to retrain, but that means you have to retrain on every single environment every time you deploy a robot. And that's just not scalable. So as you're getting more and more robots in the field, you just can't be doing that if you want to scale your business to thousands or millions of robots if we're dreaming big. So we just need to really make sure that we're generalizing. People are really good at generalizing. We can walk into any factory and we generally understand what's going on. Our goal is to make it so a robot can do the same.
That's awesome. Andrew has asked, what kind of hardware do you use for edge processing for the purpose of computer vision, or do you make your own?
We definitely don't make our own. We're not a chip manufacturer. So we do have an industrial grade computer mounted inside of the robots. It is quite powerful. So I hesitate to call it edge processing, but edge is kind of a hazy term these days about what is and isn't an edge processor. So we're using fairly powerful computers, essentially, inside these robots, because we're doing a lot of heavy processing, especially in the vision space. So yeah, we're
cool. Thank you, Andrew. Thank you, James. I've got a question from Eric. Eric said, I work in the grocery and consumer packaged good industry. One of my biggest obstacles for robots to work in my industry is picking out small items correctly out of a bin. This is a bottleneck step for delivering products to homes. Do you have a solution to this problem?
The short answer is no. The small item picking has been and still is one of the biggest challenges in robotics. And I think there's been an ongoing Amazon challenge that's about $1 million prize if you can do it well. So as I think Jay said, start with the solutions that'll get you 90% of your return on value that are simple to do and can really be valuable. And as I said, that's one of the hardest challenges. So we don't have a solution for it yet. And I don't know that anyone really has a good solution for it.
Fair enough. And then jumping back to Lou, he said the simulation feature you described is really slick. He said, can you describe it in some more detail?
So, I mean, it's a very complicated feature that isn't just one thing. We have racks and racks of servers at our office that are continuously running simulations of various sizes of various robots, basically constantly updating and doing testing for various people. So it's not just like there's one simulation. It's a lot of different pieces.
There's two main types of simulation that we do. One is kind of physics simulation. Can the robot drive down the aisle with everything that's coming on it and the payload and, make the turns and do everything safely and not come too close to something that's not supposed to come close to. And that physics simulation is really important for figuring out, again, just can the robot drive properly. Then there's higher level simulations, the discrete event simulation, which is about saying, okay, well, what if you have 80 robots all doing jobs all the time, having to charge, having all sorts of different zones governing their traffic? Does it work? Does it work in the morning at 9 o'clock when it starts? Does it still work at 2 in the afternoon, or has it run into traffic jams? Or do you have enough robots that you're not running out of charge in the middle of the day because some have to charge while the others are driving? And so basically what the simulations do, like James was saying in his presentation, is to try things out before you do it. Because to try something out can be expensive for you if you're interrupting your operations. And also, you can't just do a task. You can't just say, oh, okay, well, let's just change our zones and try the robots differently today. And so being able to do this in advance of the purchase, so you could buy the smallest number of robots that gets the job done, and then do it for continuous improvement purposes over time is important. And so there's probably other technologies that James got in his mind that I don't, but the physics simulation and discrete event simulation are the two main ones that we look like.
What does the future of your company look like? What does 5 years from now look like? Robots with arms, Samir. That's what it looks like.
I'm going to throw this one to Jay.
Yeah, I knew you would do that. Well, I mean, this is an NDA presentation, but I think that we'll find that the robots will be in more places. They'll be doing more things, have greater skill sets. Like we already talked about one skill set from just driving around flat things to having, skills like forklift, right? That's one advancement. I think you'll see much better ecosystem integration for everything from the workflow management to the automation equipment that a robot might drive up to the attachment that the robot has, to the robot itself, and then off in connecting the other way. So I think you're just going to have a much more turnkey, integrated type environment over time. I think you'll see more form factors of robots, more custom built towards particular sizes and shapes and weight classes. I think you'll see greater adoption globally. Like right now, I think there's still certain pockets of adoption that they're not necessarily everywhere. You'll see evolution in standards, right? We have the first robotic, AMR safety standard out now. Before we were having to kind of work with AGV standards, which are an approximation at best right now. And so just off the top of my head, things that you'll see changing in the future with not just auto, but the whole industry.